Hello.
Hi, Dr. Hoang. How are you?
Hi, Rami.
Yes.
Oh, okay. Thank you. Yeah. So, all right. Let's see. I need to share my screen somehow.
Oh yeah, 1 second. No, you should be able to share a screen.
Oh, yeah. Can you hear me?
Yeah, I can.
Yeah. Okay. All right. Can you see my screen now?
I can. Yeah. Yes, sir.
Okay. Let's see who's coming.
I'm going to go on audio and video mute in the background. So if you hear anything from me, it'll just be because your
Yeah.
audio your audio video something's
Yeah.
not working correctly. So whenever you're ready to start, go ahead and start.
Right. Okay. Let's see if somebody else coming. No, they're not coming.
Sure, we can wait. Sure, we can wait.
Yeah. Wait a minute. Let's see. Hey, Tuan. You're saying something, Tuan? I can hear you. You muted. All right. Yeah, I think we can start to keep the time up. Otherwise, it's going to delay. Or whoever come in there, they can join. So you can disable the waiting room, right?
Yes, it's been disabled.
Right. Yeah, so we have quite a few people coming in here.
Yeah.
Yeah. So let me start. So yeah, thank you, Rami and Cody, probably is not here, for organizing this seminar. And the title of my talk is that the electronic and photonic nanomaterials for future generation of nanophotonics. And there could be a different language here, but I hope by the end of the talk you will have some idea about this electronic and photonic nanomaterials. And yeah, so let's see. I don't know why it cannot. Here it is. So here's a picture of my lab, an electronic and photonic nanomaterial lab. It's located in Manninghorn, room 107. And yeah, there's a lot of things going on in the lab, and you can see there's a lot of equipment, a lot of setups. And this, I believe, it's a more advanced optical lab in the Mid-South regions. In the country, it's nothing, but in the Mid-South region, I mean, in Western Tennessee and several neighboring states, I think it's a more advanced optical lab. Yeah, so what do we do in the lab? So our research interest is, of course, is nanophotonic, which is the topic of the talk for today. And the nanophotonic, in my view, it has several components. Okay, so at least for my interest, there are two main characteristics. The first one is active nanomaterials. For example, like for nano-sized semiconductors or organic molecules. The material that can be used to either for emit lights or it can be used for some electronics purpose. And then on the other category is some optical platform, like optical nanocavities or metamaterials. That kind of a platform that can be used to manipulate the light. You know, manipulate the light, either the light propagation or light absorption, emission at the nanoscale. So yeah, so basically we have a two aspects. One is to the active nanomaterial to generate light at the nanoscale. And then we have other one, which is optical platform that can use to manipulate that light at the nanoscale, right? So the idea of our lab is that we integrate with nanomaterials with the optical platform to enhance properties. So this come in the physics of the light and matter interaction at the nanoscale. Okay, so that is it's really fundamental research, and of course we try to find certain property that is useful for application in industrial. So the first question is that what is nanophotonics? Nanophotonics, by the definition of the National Academy of Science, it's a science and engineer of the light and matter interaction that take place at the nanoscale, which is smaller than the wavelength of light itself. And the manipulation and modification of the light at the nanoscale, it can lead to a number of the properties, a number of the of things that can be done. For example, we can manipulate the optical property based on the size dependence, or enhance the optical fields at the nanoscale, and therefore can enhance the light matter interaction, for example. So here you can see a schematics of a device which is by the group in Netherlands. So basically what you can do is that you can have a light beam coming in. So you have its size, the structure over here, and then the light can propagate along the tip, and then it can interact with these gold nanoparticle, and then it can interact with the one of the quantum emitter at the end of the array. And then that quantum emitter, it turn out to emit the single photon, for example, that can be useful for quantum communication. So basically, you can engineer the structure to obtain the properties and the signal that you want. And the nanophotonic can have a lot of application everywhere, basically in communication and quantum information and nano lasers and LED and so on. You can see a list of the application of the nanophotonics. And it turned out that the nanophotonic is not just for physics or not just for chemistry or engineering, but it's combined with all. So, you know, the nanophotonic, it can come from physics, it can come from chemistry, it can come from material science. So basically, it combines a range of scientific challenges and application. So that means there's a lot of room for everybody to jump in. And a few words about its active nanomaterials. So the active nanomaterials here in my research mostly are the semiconductor. And semiconductor can be useful for electronics application, and also useful for optics application. And active materials, it can be like in 0 dimension, like a quantum dots, or it can be like 1 dimension, like a nanowires, or it can be 2 dimension, like a monolayer dichroic, like recently discovered. And these materials typically it have at least 1 dimension, which is in the order of 1 to 10 nanometers, and that's why the name of nanomaterial is coming in. And they have a lot of application. For example, single photon source for quantum information, and for nano laser and sensor detector. The point is that okay, you can find this kind of application probably in other kind of materials, but for nanomaterials, it's much more efficient. Okay, and for certain things like for single photons, it only comes from like a quantum physics. It only quantum from the you cannot find them in the bulk material, for example. And of course, for this kind of application, there's a lot of room to improve if we are using the nanomaterials. Now, they have a lot of property that is very useful. For example, I take the quantum dot as a case. The quantum dot, it has a piece of semiconductor, and it have the size from 5 to 6 nanometers, right? So when you go very small size, then it be quantum effect, and the energy level in the quantum dots is changing with different size of the quantum dot. And so basically you can have, for example, on the picture on the right here, you can see the different quantum dots, different size. So they have different color because the energy level in these quantum dots, they have different values. Basically, they absorb light, different frequency. And they have a very attractive feature for nanophotonics, for example. It is very photostable. You might heard that, that quantum dots TV, for example, is usually quantum dot at the light emitting diodes, and it's wavelength tunable. You can tune them for different wavelength, as you see up here. They have different color because they have different wavelength, and it can be used most importantly as a single quantum emitters. It can emit like a single photons for use in quantum information, for example. So it has a lot of potential and a lot of interesting properties that really designed mostly in quantum science. But on the other hand, the quantum dots and basically nanomaterials in general, they have some drawback and which is a problem. For example, when the quantum dot, when emitting some light, they're going to emit in 3 directions, right? So if you want to collect a photon that emitted by this quantum dot, the chance that you are collecting by looking at a given direction is very small, because you can catch only very small portion of the light emitted by the quantum dot, and they're very slow. It take a few tenths of nanoseconds for the quantum dot to emit the photon, and they have very low efficiency. So when you excite the quantum dot, not all of the photon that's going to get out, some of them will get lost, and so on. And then if you think about it in an optical lab, if you have really the advanced optical lab, you have a quantum dot emitting a photon, and you want to catch it across an optical table, and the chance that you can detect a photon by very advanced camera is still less than 1%. And then if you really want to build a device from such a quantum dot, then it could be a big problem because they have a so low efficiency. And the idea that actually the main idea of my research is that, okay, so we have to have some mechanism or some sort of optical platform to enhance these properties, not just for the quantum dot, but for nanomaterial in general. And the idea that we are going to use an optical platform, in this case, we are going to use what we call the optical cavity. For example, what you see here. The idea of the optical cavity is that if you have a cavity, which I can explain later what it looks like, and if you are putting a quantum emitter, like for example, like a 2-level quantum emitter inside that cavity, and the physics that happen in such a situation is that which is effect on the Purcell effect. And this is the picture of the guy, and he won a Nobel Prize like 70 years ago for this effect. And the idea is that if you have a quantum dot, for example, in free space with no cavity, then you will see that the quantum dot is going to emit light in all 3 directions, like what you've seen before in my previous slide. But then if you put a quantum dot in a cavity, it turns out that the quantum dot in the cavity is going to emit a lot of light, and it's going to emit in a specific direction that based on your design, right? Based on how we design the cavity. So the photon from the quantum dot emits in a specific direction that enhance both the efficiency of the emission and also enhance the directionality. So it make it easier for you to catch a photon from the quantum dot. So that is one kind of example. Now, so how an optical cavity look like. Okay, so here I give you a bunch of examples of optical cavity, and in this case they are just the nanoparticles. So in this case, made of, for example, made of gold or silver. I will explain why I have to use gold and silver later. But this particle, like either a nanosphere or nanorods or nanocube or nanostar, they act like a cavity. The reason is that when light it incident on one of these particles, and the light will get trapped in the particle, and then the electromagnetic field at the position of the particle is strongly enhanced. And then in that case, it acts like a cavity. Okay. And the physics behind it is that, for example, I need to explain what is called the surface plasmon. So the surface plasmon, for example, is we have a piece of gold, for example, or silver work the same in this case. So have a piece of gold, and then the gold is a conductive. So they have a lot of electrons, and then the electron is going to oscillate at the surface. They call the surface charge. They're going to oscillate at a given frequency called the plasma frequency, and this frequency is going to interact. So this collection of charge, it moves back and forth. So when the electron is over here, it have a negative charge here, but it have a positive charge over there, because the electron it have oscillate back and forth. So at the position that the electron stay, it's negatively charged. At the position that the electron did not stay, have a positive charge. So it forms something it's called the surface plasmon, right? And now if you make that object, it's very small, like a nanoparticle in this case, which is typically smaller than 100 nanometer. And then the charge, normally it distributed uniformly around the particle. But then when you have a line that shine on it, for example, take a flat line or any kind of line you shine on it. So this charge is going to oscillate back and forth. For example, here it oscillates up and down, and it forms some sort of something similar to what you see up here. And in this case, we have something we call the localized surface plasmon. It localized because it bound to the surface of the nanoparticle, and then if you look at the function of time, you can see that it moved back and forth, and then it formed something we call the surface plasmon. Okay, and like I said before, when light hit on this nanoparticle, they go to trap, because they are interacting with that surface plasmon, and it got trapped in that particle. And then it turned out that it's going to enhance the optical effect. So it enhanced the electromagnetic field surrounding the nanoparticle, and then it enhanced the optical effect. And then we can get use of that enhancement. Okay, so that's what I'm going to tell you next. So in one of the first example that we try to use the properties. Let me show you one example. So in this example, we have a nanocube, for example, made of silver, and we put it on top of a gold film, as you see here. And like before, underneath of this nanocube, and between the nanocube and gold film, the electromagnetic field is going to oscillate. The charge is going to oscillate up and down, like what I draw in the cartoon on the top right here. And then it forms a plasmon mode, a surface plasmon, a localized surface plasmon in between the nanocube and the gold film underneath. So in practice, in the actual sample, it looks like it to have a nanocube on top of the gold film. So this is an STMC image of the sample. And the thing that's really interesting is that in the area, in the volume between the nanocube and gold film, the electromagnetic field is very enhanced, it's very strong. Okay, so we want to get use of that. And so in real life, it looks like this. If you look under a microscope, each of those nanocubes is show up like one red dot that you see in this image here. So each individual dot there corresponding to 1 nanocube on top of a gold film. So you see there are many of them, and they are well separated. And on the left here, you can see some COMSOL simulation. So you can see for different electric field and magnetic field component of the electromagnetic field underneath the nanocube. And we are going to get use of that field enhancement, like I'm going to see the on the next slide. So what you're seeing here is that the same structure again, but we are going to put some active materials into that gap. Like I said before, the gap is only about 10 nanometer or so. So if you want to put something into that gap, the gap has to, the material or whatever you put in there has to be really small. And that's why we have to use nanomaterials. In this case, we can use quantum dots, cadmium selenide quantum dot, or we can put the 2D material into that gap, or we can put some dyes molecule into that gap. Okay, so that's just what we did. So what you see here is a kind of schematic of the sample that we made. So we have a gold film and we put the nanocube, and in the gap in between we put the quantum dot into that gap. And what happened is that the quantum dot that underneath the cube is going to act differently than the other quantum dot that not underneath the nanocube. And bottom here you can see an actual sample that we made. We have a nanocube and we have a quantum dot show up at the type of dark dots. And on the nanocube itself, we have the size about 75 nanometers. And the quantum dot have the size like about 5 to 6 nanometers, like I said before. And here on the right, you can see the light emission. So this measures the intensity of light as a function of the wavelength. So we see the quantum dots underneath the nanocube. It's very enhanced, very strong compared to the quantum dot on the glass. So you see that they are much stronger. So in the best case, we can get up to like a more than 2,000 enhancement in the photon that emitted by the quantum dot underneath the nanocubes compared to the quantum dot on the glass without the nanocube. So they are much intense when they are coupled to this nanocube, which is enhanced by the surface plasmon, like I said before. And then we can also measure the decay time from these quantum dots. So we see that for the quantum dots, so this is function of the intensity versus the time it takes for the photon to get out of the quantum dots. So in this case, for the quantum dot on the glass without a nanocube, you see that around 10 nanoseconds. And for the quantum dots on the cavities, you see that the decay time is about 10 picoseconds. So you see that 1,000 times faster. So to get a very quick demonstration, we put the quantum dot in the cavity, so you can make the quantum dot like 1,000 times brighter and 1,000 times faster. So we can use it, for example, for like an ultra fast LED. If you will, try to make an application out of it. And also, if you want to think about like to make a single ultra fast photon come from this quantum dot, we can try to reduce the quantum dot density on the sample until that we have only one quantum dot beneath the nanocube. And then if you have one quantum dot only able to emit one photon at a time, and we use a setup we call the anti-bunching measurement, which we can kind of do the start and stop. So the graph down here shows an actual sample that we see that the nanocube and they have the quantum dot is very diluted. So we hope that there's only one quantum dot underneath the cube, and then we do the anti-bunching measurement. The curve here is showing that there's a dip at the 0 time difference between the two detectors. The dip will tell you that at the 0 time delay between the two detectors, there's no. So that means the photon has to split into like APD1 or APD2 with two detectors. It can come either to APD1 or APD2. It cannot come to the same two APD at the same time. So that means at the time delay at 0 between the two APD, you should get no photon, and that's exactly what we're seeing here. Okay, so basically we demonstrate that we have a single photons emitted by the quantum dot that couple to the cavity, and we also compare with the case that the quantum dot on the glass. So you see there, they also have a single photon, but it's much slower. And then in this case, you can think of, okay, we can use the single photon source, like ultra fast, for quantum information processing, for example. And with this kind of nanocube, we can also do more research out of it. For example, in this case, I saw plasmon-assisted nonlinear optical generation. For example, in this case, we have an array of quantum dots, array of nanocube. In this case, we don't need the quantum dot. So we can hit the laser with the frequency of omega. So this surface here, it have an array of nanocube on top of a gold film. And in between, we have very thin, like about 3 nanometer zinc oxide layer. And then we observe that the second harmonic generation from such a surface is much stronger compared to the case that if there's no nanocube, okay? And then we see like up to like a 10,000 times enhanced in the second harmonic generation that is enhanced by the nanocube, okay? And we can also look at an array of nanoparticle which is not cube. Like, for example, we have an array of particle here. We can have a circular, like a kind of circular disk. And these arrays of circular gold nanoparticle, they also exhibit some sort of a plasmon, but in this case, it's surface lattice plasmon, which is a collective behavior of many particles, and they have a resonance. We can also use that for our application. In this case, we try to make a nano laser out of it. So this is an actual device. So we put some dyes, molecules into that array of particle, and we hit that with laser, and we see the signal coming out. We demonstrate the lasing behavior, and then this lasing signal can be tuned back and forth based on the dielectric environment that we put into the solution that cover the array. So basically, we can make a nano laser out of this plasmonic nanostructure. And another approach, we can also use some other structure. For example, we have a nanostar. A nanostar have a bunch of spikes. Okay, so this one of these spikes is very tiny. It have the size of less than 10 nanometers. So when you hit light on those nano spikes, the light is going to get trapped into that tip, and it creates some sort of hotspot. And then if we have many of those, nanostar, and then if we hit a laser on it, and it have some dye molecule in it, and then the dye molecule is going to emit some light and going to scatter back and forth, and then it creates some sort of coherent random lasing. So this is a new phenomenon, and that's exactly what we did. And we kind of go beyond that. What we did is we take an optical fiber, a bare optical fiber, and then we coated the optical fiber with a nanostar, and then we put that in a dye solution, and we can excite that tip with a laser, and we can get the lasing out of it. So basically, we demonstrate the lasing from a tip of an optical fiber. So this is really nice, because you can directly have an application of this device that you can use it for, like for sensing, for example, like a remote sensing using the nanostar on optical fiber tip. You know, you just change the dielectric environment, and then the lasing peaks is going to shift back and forth. So that can demonstrate the sensing behavior. And here I want to show an example of the lasing from the nanostar that is coated with an optical on optical fiber. You see that. So here are the emission spectra, which was taken at different excitation power. So you see that at low excitation power, it shows very broad emission, but then when excitation go up, it shows very narrow peak, which indicates lasing behavior. And basically, we can demonstrate it in real time, actually. So it's really actually a working device. Finally, I think I'm finished very soon. So we also use this plasmonic nanoparticle. In this case, we have a gold nanorods, and we have like a combine this gold nanorod with an exosome, which is it's something that is generated by a body of a human body, and it could cancel it could carry the sign of the cancer, right? So we can use that technique. So we use a plasmonic properties of the gold nanoparticle, which in this case is a nanorod, so we can detect the cancer, the tumor cancer exosome at the very early stage. We can detect them at really like a early state, like a state 1 for state 2. So we demonstrated that. For example, in this case, I saw the what we call the surface enhanced Raman's image, right? So you see the real each of these dots you see on the right here is from a patient, an exosome from a patient that have a cancer of level 4, stage 4. And on the left, you see an image from the Raman image from a exosome from a patient which is healthy. So you can see that clearly different in the Raman signal from the two different patients. So this research has been supported by NIH to allow us to detect the cancer at the very early stage. So as I know I have only 30 minutes, so I would like to jump to conclusions. So basically what we do is that we tailor the light matter interaction at the nanoscale. In this case, we try to combine an active nanomaterials with a plasmonic nanostructure. So we demonstrate very fast, very strong light source, and we demonstrated the enhanced spontaneous emission and stimulated emission, which is lasing that I saw before, and we saw the enhanced nonlinear optical processes. You know, one example I saw was the second harmonic generation, and we saw an on-chip tunable laser, and also an application in biophotonics, which is using the plasmonic nanoparticle to detect cancer. Yeah, so in the future, we are interested in moving into the direction that we want to study some basic thing. For example, the energy transfer between the nanomaterials as supported by the surface plasmon, and we want somehow we can control excitonic state in the nanomaterial at the single emitter level, like a single quantum dot, a single molecule. And of course, we still have the cancer detection project going on. And yeah, so the lab is well equipped, and we have a student working in the lab, and we have even like a high school student where we have a project all year round. For example, in this case, we have a high school student. They are playing with the butterfly wing, and they kind of like try to look at the different absorption and reflection from the butterfly wing to see how the color of the butterfly wing is where the color come from, right? So basically, the high school student are really interested in it. So in the bottom image here, you see an image of the quantum dot, like probably billion of quantum dots. Each of the dots there is an image of it. The photoluminescent image come from a single quantum dot, which can be used for like a single qubit, like I mentioned before. Yeah, so in the end, I like to acknowledge a group member and funding agency and collaborators. And all right, thank you very much for your attention. So I think there are quite a few people sharing the same account, and they look at the so we have a more than I guess we have more than six audience in the room. They share the same account somehow. But anyway, so I finished. If you have any question, you can go ahead and ask me now. Rami.
Yes, please. Yes, thank you,
Yeah.
Dr.
So anybody has question, you can start.
Yes, please. If anyone has a question, please feel free to ask.
Yourself. Hey, Tuấn.
Hi, Thang. Very nice talk. Thank you very much, and also very beautiful work. I have few questions.
Right.
First, do you hear me clearly?
Yeah, I can hear you. Yeah.
Okay, that's good.
Yeah, very
The
well.
last
Yeah.
time I don't think that better. I have question. So for plasmonic, you say that it mostly come from the metal to metal surface or from metal to like gold to gold or gold to silver. Is
Right.
that possible to see the plasmonic from the metal to dielectrics, for example, between the tip of the gold and also the 2D material?
Yeah, certainly. So actually, the plasmonic have two consequences. One is the thing that I saw there, they enhance the properties of nanomaterials. But on the dark side, the plasmonic nanoparticle, it kind of like it quenches. So if you have a nanoparticle with a very sharp tip, and if that tip is touching directly with your 2D material, and then what happens is that it going to quenching effect. So let's say you generate an exciton with an electron and hole pair in your 2D material, and then that electron hole pair is going to be captured by the metallic particle. So in that case, you're going to quenching effect, which is unwanted effect, right? So I'm not sure that is a question or something else.
Yeah, that is kind of question. That kind of answer to my question. So you said that the tip is that taking electron or transfer electron into the 2D material, right? In that case,
It mostly it take away the charge from the material because the metal is kind of unlimited. They can get a lot of charge.
Okay.
So basically, when you generate an electron and hole pair in your active material like a semiconductor, for example, and then it takes some time for those charge to be recombined into light.
Okay.
So before the charge they recombine, the metal already captured those charges, right? So that is typically what happens. So in practice, what we do is that we have to have a dielectric layer that separate the active material from the metal surface. So they are not in direct contact.
Okay. So it look like it quench, it not enhance.
Right. So if you make it dry, then it will enhance to prevent the quenching, but it enhance more.
Okay.
If you don't do it dry, then it will be quenched more. That is kind of like engineer the structure. That's right there. Right.
Yeah, very exciting. Yeah. So another question about the single photon emitter.
Yep.
You showing that the quantum dot is a good shot of the single photon emitter, right?
All right. So yeah. So let me go back to the anti-bunching caveat that there.
Yes. So what I understood that the quantum dot has to be well defined energy state.
That's right.
If the photon emitter is also well defined.
Right.
But some of the quantum dots, they have degeneracy. For example, right. in the low state, right? They have several degeneracy. How is that affect the single photon emitter? For example, you don't emit one photon, but you can emit several photons at once because of this. Yeah,
that's true. First of all, if you emit the several photons at once, you have to go into different regime of pumping it. You have to excite quite harder. So in this case, like for example, by acetone, you have to excite the laser with slightly higher power. So in this case, we have to be the linear regime. That means we excite linearly. So hopefully there's a single photon. Now, if you excite a bunch of other stuff, of course, I'm sure there are. But then, so basically you don't get very clean single photon source. So you look at the deep here, ideally it should be 0. And we didn't get that quite 0 actually.
Okay.
So that means the single photon source here is not really clean single photon source. I have to be honest, right? And of course, we tried like 100 of them, not all of them working. Yeah, because you're not sure there's a single quantum dot underneath it. You cannot see through it. Maybe like one or the quantum dot nearby here might also affect, for example. So we try like many of them, right? So to be honest, it's a kind of fundamental research. So we try to get a good one and then we kind of publish it. But to be practical, then you have to have a better way controlling it.
I see.
So I agree. We could have like a multiple photon, or it could be like a nearby quantum dot. So we don't have to really clean single photon sort here. But the principle, if you have a zero below 0.5, then you can't claim that single photon sort. But it's not so clean. I agree.
Yeah. So what temperature do you use?
Oh no, this is room temperature.
Oh,
So this is cadmium selenide quantum dot. They work at room temperature, right? Yeah.
Wow.
Yeah.
What is the broadening of the emission? Is that very sharp or it's very broad?
Oh, the quantum dot they're quite broad actually. So the line width I forgot, but for the single exciton of the cadmium selenide quantum dot at room temperature, it's about like a 35 electron volt, and the thermal energy 25 electron volt. So the single exciton survive at room temperature.
Okay.
Yeah. So it's lighter than the thermal energy, so they still survive. But they're quite broad. I agree. They have a few MeV. It's not like a solid state quantum dot. It's totally different story.
I see.
Yeah.
So the last question is this it corridor or it's epitaxial growth quantum dot?
What is that?
Is it corridor quantum dot?
Yeah, it's colloidal quantum dot. It's commercial. We just buy them from Sigma and Rick. Yeah.
Okay.
Yeah, it's quite cheap. You can buy the bottle. You can use one time.
Did you do any treatment before doing?
No.
No.
There's some technique that you have to make sure that the quantum dot and nanocube they stick to the surface. It has to be some sort of like a polymer, and then also some sort of surface treatment.
Mm-hmm.
Otherwise, they won't stick to the surface.
Okay.
And you want them to stick, for example, you want them to stick like separated. You don't want to aggregate. For example, here you see the nanocube have to be separated from each other. They not stick together.
Okay. So
Yeah.
what chemical do you do for the surface treatment then?
No, yeah. So we have some polymer to have different charges, either positive or negative charges.
Mm-hmm.
So for example, the nanocube is slightly negatively charged, and the surface had to be slightly positive charged, for example. And the quantum dot, they have to suspend it in certain solvent. I think a toluene or something. It's otherwise they won't stick.
Okay.
Or even if they stick and then they go away after you put the quantum nanocube on it.
Yeah.
Right.
That's very good. Very nice. Thank you very much.
Yeah, thank you for the question. Yeah. All right. More questions from the audience. So, yeah. So I think it designed only 30-minute talk this time. So we have went over the time. I'm sure, Rami, can we stay for a few more minutes, or we need to run?
We can sit for just a few more minutes.
Yeah. So yeah, in case somebody else have a question. All right. So if not, then thank you very much. I will have another talk next week at the University of North Texas.
Okay.
I probably will go more detail into. So today it's kind of for general audience who don't have that much experience in this physics or in this kind of research. But next week I will have a talk at the University of North Texas. Which I will go into more detail, technical results and more deep into physics, because there's going to be like a physics department over there. So I'm going to talk more detail into my research. Yeah, so it'll be like a next Tuesday.
Great. All right. Thank you so much.
All right. Thank you everyone for showing up.
Thank you.
See you around.
Thank you. Have a good day.
Bye, Tuan.
Bye.
Bye-bye.